Kolejny raz na wydarzeniu głównym Copernicus Festival. Tym razem naszym gościem jest Rovatsos i przedstawi Państwu wykład Computation, Intelligence and Society. Serdecznie zapraszamy. Dear professor, the floor is yours.
Good evening, ladies and gentlemen. I'm delighted to give this lecture titled Computation, Intelligence and Society today as part of the Copernicus Festival, and indeed very grateful to the organizers for inviting me to speak at this wonderful event. In this lecture, I want to explore the relationship between computation, intelligence and society against the background of the profound transformation new digital technologies are having on our lives. I will focus particularly on artificial intelligence, an area that has recently been receiving much attention in public debates, both in terms of the expectations placed in its ability to bring benefits to society, and in terms of the fears surrounding its potential negative impacts on humanity. In developing the ideas and arguments I want to put forward, I will assume the rather pragmatic standpoint of a computer scientist, which is sometimes overlooked in some of these debates, and I will contemplate the implications that assuming this perspective has for our vision of the future of humanity in the face of the developments around technologies like artificial intelligence and what they will mean for our world. As you will all be aware, the emergence of digital technology is widely seen as the so-called fourth industrial revolution. It is transforming the ways in which we live and work, and the ways in which we interact with each other. And we can expect that this transformation will continue as ever more advanced technologies continue to be developed. Some of these changes are very tangible and are already having a profound effect on our ways of life and society as a whole. We can now all communicate with anybody in the world. We can access enormous amounts of information online and buy almost everything we desire without leaving our homes. At the same time, we are worried. We are worried that our children might want to become social influencers and not astronauts. We might worry that we are watching videos of politicians, speeches that are not real, and that we might be denied health insurance in the future just because we are looking up information about chronic diseases online. It's not surprising that, when the world changes rapidly, we witness new developments having positive and negative effects. In fact, it's hard to think of any human invention without finding that it has both had a positive and a negative impact on the world. If you think about anything from, let's say, chocolate to banks and financial institutions all the way to airplanes, you will certainly find there are always good and bad things about these things. Nonetheless, when it comes to artificial intelligence, or AI as we call it, people seem to be either more excited or more concerned about AI than about almost any other technology. As some of the capabilities we would normally assume to require human intelligence, or sometimes what we could call animal intelligence, it is often viewed in some ways as the pinnacle or maybe even the final step of the digital revolution. A vision of machines that can do the things only humans have been able to do in the past conjures up images of a future where we might be controlled by machines smarter than us and more powerful than us, and of scenarios where these machines bring about either some kind of utopia or, conversely, maybe even the destruction of humankind. I've worked in AI for over 20 years, and I have been involved in many of these debates, which seem to become more and more prominent as the field is advancing. But I'm still not quite sure whether AI does require a step change in how we think about our future, or whether instead we just need to deal with it just like we have approached other technological innovations in the past. And this is the key question I want to explore in this lecture. Not to offer a definitive answer, but to lay out some considerations that I hope you will find helpful in terms of understanding the wider debate. Before we talk about AI as such, it is important to remind ourselves of what computers actually do and what they are capable of. Since 1936, when Alan Turing proposed the Turing machine as a universal model for what digital machines can actually compute, we have been developing all computer systems based on this model. It is basically a device that can read and write symbols that encode information onto a tape, and that can perform simple manipulations of these symbols using these algorithms, these sets of instructions that are also stored on the device. So whatever your impression is, and what you might be hearing about the marvelous capabilities of AI, everything we can do with computers today is still predicated on this very fundamental idea. This, while I'm describing it maybe as a limitation, as something that sounds quite simple, in no way should diminish the value of computing. In fact, I think we can say it has indeed been a groundbreaking invention that has transformed the way we think, because for the first time in history, it gave us a universal tool for translating our ideas about how to solve a problem into the language of machines that can perform simple calculations. The way we go about that is through programming. Now, you may not be familiar with programming, and I don't want to teach you how to do it in 10 minutes, but I want to explain a little bit what we do when we program a computer. We apply our understanding of the world to encode a function in a mathematical language that contains instructions for how to perform a calculation on a machine. Consider, for example, the snippet of code that I've put here on the slide, and which can be used to calculate the square root of a number. This uses the so-called Babylonian method, a very old method that people used to calculate square roots long before computers existed. And it's not important how it works exactly. The key thing here is that we have a definition of what we're looking for. We know that the square root of a number is the number we can multiply with itself to get the original number. And we need to translate that to a sequence of steps that can be performed on a digital computer. Now, the way this is computed is based on iteratively summing some numbers and then performing a couple of divisions until two numbers are roughly the same. The interesting thing about that is this piece of the computer program is based on how humans perform this calculation. In fact, the pocket calculators you all use and the algorithms we use on computer to perform this operation is actually very different. These methods used on our calculating machines do this in a different way by computing a long sum of polynomials divided by factorials. So you may wonder why I'm going into this very simple example into so much detail, but it's essentially to make an important point, namely that the methods that we might use on machines might look very different and behave very different for solving the same problem from those that humans would actually use. And why is that? Well, I want to argue that is because humans and machines and what we could maybe call their intelligence are fundamentally different. Let's now think a little bit about how what I've just described compares to how we use other tools. So let's take the example of a hammer. The way we interact with a hammer is, as we would say in computer science, sub-symbolic. That is, it does not involve the exchange of explicit information through symbols. Our knowledge of the hammer and of how it should perform its task was encoded in the physical design of an artifact, actually even long before we understood the physics behind it. We didn't know the laws of physics that were needed to make a hammer work, and we learned how to manipulate it, and we still learn that in very physical ways. We do that with our hands and our arms, and this is guided by a very complex process in our brain, but it doesn't involve any type of language or any type of symbols that have any meaning. What is more, actually the way we combine our intelligence with the capability a hammer gives us has been deeply embedded in our brain through observation, through practice, through feedback from the physical environment, and we would actually find it quite hard to put into words what exactly goes on inside us when we are using a hammer. How our muscles are moving, how we observe what is happening in real time, and how we maybe correct some mistakes when we're going the wrong direction, and respond to the effects of our actions. Now, in some sense, we can imagine that a computer is like a hammer and think about what it means to use computers and how we learn to use these tools, except there is a fundamental difference. The programs we can write on a computer can represent all kinds of tools, not just something like a hammer that is built for one specific use. And because these computers are very different from us, we can't just tell them what to do as we would maybe tell a child or another human. We have to use our intuition on how the task needs to be performed and to translate it to their language to make them do what we want them to do. Now, turning more towards AI, here we want the tasks that are performed to replicate the capabilities in humans and animals that we assume to require intelligence. And as the quote at the bottom suggests, when we do that, this is a creative and constructive process to shape an artifact, and less a process, I would argue, of trying to understand how we think, which, by the way, I also generally think we are not particularly good at. Now, when we work with these machines, we have to start thinking computationally. We have to start thinking in terms of bits and bytes and instructions and algorithms in a quite artificial way. But in return for that, we obtain very new capabilities that are distinct from ours. The ability to perform millions of calculations in a second, the ability to store almost unlimited amounts of information, and to communicate and exchange this information across millions of devices around the world. Now, when we think about how we can use these machines to emulate intelligence, what does that actually mean, and what is required to achieve it? One important thing here is that in the space of all possible programs we could write, we are looking for those that would be smart. Now, imagine all possible sequences of instructions in a programming language like the one I showed you before, and all the possible assemblages of computer hardware we could put together. This creates a plasticity that is enormous. And even though it's vastly more simple than that of the brain, gives us almost limitless opportunities to shape and use for different tasks. Now, the project of AI, which started in the 1950s, but builds on an age-old dream of understanding and replicating the human mind, is very much about the question of what those programs look like that will enable computers to do smart things. So we're not interested in the ones that simply search for a name in a phone book or that simply add numbers. We are looking for the ones that are smart. So how could we find those, given that we maybe don't really understand how the more complex products of intelligence are produced in the human brain or in human society? In the early days of AI, the dominant paradigm was to come up with general problem-solving algorithms which we would feed human knowledge into. For example, in terms of an algorithm that could process rules expressed in a language that humans can read, a mathematical language, usually some form of logic. And the idea that if we have the right way of processing these rules, then we would produce correct inferences, we would produce correct conclusions from the human knowledge we put into the system. Of course, that would happen without necessarily the machine understanding what all that knowledge means. It would be very far from what we take human understanding to mean. The second approach was to learn the program from the data. This is very different because here we use an algorithm that will learn to reproduce patterns observed in nature. In other words, again, we have some general algorithm that we can use to guide the search for the right final program, which we need to solve the task we want to solve, by going through lots of alternatives based on how closely these alternatives match what we're observing in our data. This is what we call nowadays machine learning, and it comes in many shapes and forms, among which neural networks are one of the most popular ones at the moment, and I will say something about these later. Now, many people think rule-based systems are old, knowledge-based systems are old, and machine learning systems are new. It's quite interesting to observe that both ideas came about at around the same time. Marvin Minsky, shown here, one of the fathers of AI, built the first neural network, still consisting of cables and quite mechanical, in 1957, to mimic a very simple brain-like structure, basically a network of cells that propagate signals to each other. If you give this network some inputs and outputs, some signals, and you tell it what it's supposed to produce on what kind of input, the network adapts the weights between these cells, which is inspired by what happens in the human brain, in order to replicate the pattern you gave it. On the other hand, the first paper, the first publication on programs that could develop common sense by processing machine-readable human language and using logic was published by another of the great fathers of AI, John McCarthy, in 1959. So you can see that the idea of using language and logic and mathematics on the one hand, and the idea of looking at the brain and trying to replicate that structure and focusing more on experience and observation are both ideas that people naturally came up with very early. And from that, two schools of thought emerged that fought long and hard, and to some extent they're still fighting. At the moment, machine learning has the upper hand, but many AI scientists think that for the next innovations, we're going to need a mix of both. What does this mean, I want to ask, from the standpoint of human experience? It's one thing to say, these are the systems we build. How does that feel to the people who are building the systems? From my point of view, I want to emphasize that this is very much about how we communicate with these machines, and that how we communicate with them shapes the idea we have regarding the combination of human and machine intelligence. And it is in this regard that the two approaches are radically different. In a knowledge-driven approach, we tell the system what we know about the world, whereas in the data-driven one, we feed it with observations. This reflects a fundamental difference in terms of the underlying epistemology, if you like, the theory of knowledge, in terms of two approaches reflecting, one could say, an idealist versus an empiricist position. And, of course, this is not new in computer science. Philosophers have been thinking about whether we get our knowledge from experience or from thinking from many, many years. And the question is then, what do we know that we can tell a machine? Or, alternatively, how does data that we feed into it actually represent reality accurately? I would argue that in both cases, we, of course, filter this through our understanding of what we know or through our interpretation of what we observe in nature. Now, I want to go back to a practical view and say that a programmer might actually not care about these philosophical distinctions. From their standpoint, what one would consider intelligence has three components, I would argue. The first one is, how hard is the problem? how much intelligence do we think it requires? Finding someone's phone number in an international phone book with 5 billion entries is certainly impossible for a human, but we don't think it requires a lot of intelligence. We probably think it requires more computational brawn rather than brain. The second element is how much do we understand about how we solve the task in the detail. We can have intuitions about how we solve intelligence tasks, but it may be very hard to fully explain or reproduce what we think. A good example is translating a piece of text. Most competent speakers of 2 languages can do this quite well. Take a piece of text and translate it to the other language. But we actually don't have a good theory about how we do it. We don't even really have a good theory about what makes us judge the quality of a translation somebody is showing to us. We do these things quite intuitively, but we don't have access to how we do it. Finally, there is a question, and I think this is the third element in this process, which is how little do we need to put into the system when we design it? Or, alternative, you can think about this in terms of how good is the solution given how much or how little effort we put in as humans. For example, you can ask yourself, how smart is a reasonably good chess-playing program if we've only given it a handful of rules? In these cases, do this sort of thing, in these other cases, do that sort of thing. And maybe it doesn't always win, but maybe it has reasonably good performance. How smart is that compared to a different system that we have fed with information about millions of human games to identify the right move in almost every possible game situation? So the question really here is intelligence relative to effort or relative to the resources we put in? Now, having given you a perspective on what has happened very recently in AI and how us computer scientists may think about engineering systems that do smart things, I want to go back a little bit into the history of thought around understanding and replicating intelligence, and which I have mentioned predates the emergence of modern computing and AI by thousands of years. One of the first attempts to understand the mechanics of human intelligence was that of Aristotle. His key idea was to think about the patterns of human thought and to try and describe their form in terms of abstract rules. For example, if I know that Mary is human and all humans are mortal, then I can infer that Mary is mortal. Note that the rule of inference here is very general. What allows us to draw conclusions does not depend on the details of whether I'm talking about Mary and about being mortal. So the general pattern, given A, and given that A implies B, I can infer B, can be applied regardless of what A and B are. This logical rule, alongside others that have what mathematicians call universal validity, allows us to view reasoning and thinking as mathematical proof. B can be derived as a new theorem if we know A, and if we know that from A, B follows. And we can apply this rule mechanically to concepts like Mary and being mortal without knowing what these symbols mean. Whether we do this on paper or we do it with a computer doesn't really matter. What matters is that it gives us a way to create new knowledge from knowledge we already have. And that, as I mentioned earlier on, inspired knowledge-based AI and logic-based AI, the paradigm that dominated AI for its first around 40 years. You may very reasonably ask where this knowledge would come from, and how do we formulate good rules that capture what new knowledge we can infer from knowledge we already have? How do we know, for example, that there is a relationship between the fact that it's raining and that the grass gets wet, which we could then write down as whenever it rains, the grass gets wet. This is a question David Hume, the great philosopher of the Scottish Enlightenment, pondered. His radically empiricist perspective argued that all knowledge comes from observation and human experience. Therefore, a causal relationship can only be detected by observing what he called a conjunction of events. That is, observing, for example, that it is indeed raining and the grass is wet, while also maybe observing that the grass is dry while it's not raining. Arguably, you could say that if Aristotle invented knowledge-based AI, then David Hume invented data-driven AI and machine learning, almost, although these men had no idea about computers. And the great contribution of David Hume here is that he gave us a way of thinking about how knowledge actually comes into being from experience. Despite these great ideas, it wasn't until a third man appeared on the scene. You will excuse me here that I'm using famous thinkers that are Scottish or Greek, because these are the two countries I'm most closely associated with. There are many others who have contributed to this history of thought. Thomas Bayes, who was actually for a while a student at our university, was the first person who was able to translate some of these ideas to a mathematical model that would ultimately lead itself to application in algorithmic systems 200 years later. His great contribution was a calculus for quantifying how likely a hypothesis is, a scientific hypothesis, a theory about how the world works, given what we observe and given what we already know. And this enables us to connect any piece of knowledge we may consider a good representation of reality to the data we may gather from observation or experiments, and also to design these experiments in a rational way in order to test our assumptions. So in many ways, these principles are really very essential to the foundations of modern science. Simply put, his Bayes theorem provides a mathematical formula for estimating in quantitative terms how likely an event is given my assumptions and my observations. So let's say I know that 10% of all patients with a brain tumor have severe headaches, and that 0.1% of the whole population have a brain tumor. Then his theorem allows me to calculate how likely it is that a patient who presents themselves with a severe headache has, in fact, a brain tumor. Bayes' work has not only been foundational to the field of statistics, it also provides a framework for making rational decisions. If I know that I can perform another examination on the patient, but that this examination is very expensive, then the rational thing to do would be that if the likelihood that there is a tumor is very, very low, I don't spend my money on this examination. But if it's higher, I may decide that it should be necessary. The ability to capture these rules of decision-making in mathematical terms is really quite fundamental, because then we can put it into a machine. And this is key to the kinds of AI systems, for example, robots, that have to make decisions under uncertainty. They receive some information, they don't know the full truth about what is happening in the world, but they need to make choices. And they need to make choices that are optimal with respect to what they know and what evidence they have seen. In the more recent history of AI, not going back so far, many of the key figures that I have already spoken about have thought about what intelligence means in different ways. Interestingly, Alan Turing himself was very interested in whether machines can be intelligent. He had just invented this model of what computers look like, and that was one of his first ideas. Can they be smart? He proposed the famous Turing test, which sets up a purely behavioral criterion for machine intelligence. If the behavior of the machine is indistinguishable from that of a human, then, to all practical intents and purposes, we should consider that machine intelligent. In much of modern-day AI, rather than thinking about the essence of intelligence, that is, asking about the how when looking at what a machine does, focuses on this very engineering-oriented view. What matters is defining a task, for example, translating a piece of text, playing chess, or having a conversation about current politics, and simply measuring whether a machine achieves similar performance to that of a human. To some scientists, and maybe to all of you, this may seem a little bit crude, but I actually think that it has some appeal because it almost circumvents asking a question about intelligence and the essence of intelligence that could be deeply troubling or make us worry, and instead focusing on whether we can actually build things that do useful, build machines that do useful things. On the other hand, you can also have a critical view of this, and I sometimes think we should not necessarily make the comparison to humans in order to get value out of these systems. They might be much better than us at certain things and much inferior to us in other contexts, and I will return to this issue later. I will not say much more about these two gentlemen, which I mentioned before, but all I want to say on them here is that their view takes inspiration from a more Aristotelian or a more empirical view of intelligence, and to highlight that you can view this in another way, which is to distinguish between the low-level functions of the brain and what we consider to be the higher-level functions. So I find it quite plausible that the things like moving our limbs, sensing things with our skin, that these things, or seeing things with our eyes, that these things might be quite deeply embodied in our brain and in our nervous system through experience and through evolution, which might be a little bit like neural networks. But at the same time, I think then that when we perform explicit steps of thinking about the world, of making decisions, you know, who should I marry? Should I invest in this stock? Should I change my job? Then probably that doesn't happen through without some involvement of knowledge that I have in terms of words and symbols in my brain. So if you then think about human intelligence, I sometimes think we should be careful about whether any computer system can do all of these things, given how broad a spectrum that is. And this breadth is illustrated by work in more specific areas, which are all still very relevant today, and which tells you a little bit about what things AI researchers are interested in, but where the history also reveals that what we see today come to fruition actually started emerging decades ago. This gentleman, Ted Winograd, was a pioneer of what we now call natural language processing. He built ELIZA, what we could call today a conversational agent, a system you can talk to, almost 60 years ago. And in principle, the idea is not very different from what you have nowadays on your mobile phones, these conversational bots that go by the names of Siri, Alexa, and so on. ELIZA was supposed to mimic a psychoanalyst. And to do that, it simply converted the user's statements to questions using very simple grammatical rules without actually understanding any of what the user was writing. In the example dialogue on this slide, it simply asks, how long have you been afraid, when the user says, I have been afraid, and so on, using some very simple patterns of syntax combined with why, how long, do you enjoy, are you sure that, and so on. From the standpoint of understanding language, critics may argue that this is just a cheap trick, and there was a lot of criticism. He actually wanted to make a point that you can make things look intelligent without them being intelligent. But on the other hand, from a very pragmatic point of view, maybe there are contexts where having this very simple functionality actually makes sense, and you could tell the user, look, this agent doesn't know or understand what you're saying, but if you find this interaction useful, maybe if it helps you discover what the reasons are for your feelings, and it's free, it doesn't cost anything compared to a real psychoanalyst, maybe there are situations where it could be beneficial. Robotics is, of course, another great area that always has been of great interest in AI. Niels Nielsen, a gentleman who worked on planning for robots in the 1970s, he pioneered these technologies on very early systems, like the one shown here, which is called Shaky, because it was shaking a lot when it was moving around, and was used as an office robot. His idea was to develop a language that allows us to describe when we can perform certain actions and what happens if we perform those actions. And what he wanted to achieve was to be able to give a robot a goal. So not just a mechanical robot that takes objects from a conveyor belt and moves them, but actually a robot that is able to break down its task into steps and decide what actions need to be done to achieve the goal. For example, you could tell Shaky to take empty cans to the rubbish bin, and it would know that it needs to go to the can, pick it up, carry it to the bin, and drop it. Of course, giving robots and other AI systems general abilities like that requires them to have a rich knowledge of the world. And in the days where, as I said, the main paradigm was to capture human knowledge, this was a big focus. Doug Leonard showed on the right here, he embarked on a very ambitious system called Psych, where he tried to define an all-encompassing database of all concepts that humans use. This pyramid, you can't quite read it, it's too small. It basically is a taxonomy of everything from philosophical concepts to clothes and energy and sewage systems and different types of fruit. And he had a very long project running, almost far over 15 years, I think, to put this database together, because he thought once we get everything into that system, then the AI systems will know everything about the world and will be able to do marvelous things. The general view is that this project failed spectacularly, but many of the big information systems we all use on the internet today use similar ideas to make searching the web easier or to integrate different big databases with each other. Now, all these historical approaches demonstrate many directions that AI research has taken, and they also demonstrate that a lot of the things we are seeing now, even though they work much better now, are actually quite old ideas. In terms of success, all of those have been eclipsed by what has now become the dominant paradigm of AI, and which is called machine learning. As mentioned before, machine learning is about learning a program from data. In simple case, that thing I call program might just be a mathematical equation, as in the example shown on the figure here. So say we observed how many cups of coffee were sold in a coffee shop at different times of a day on many consecutive days. These are shown as red dots in the graph. And we wanted to extract a more general rule from the data. We want to understand what is the law here that describes when people drink how much coffee. Now, a possible model that somehow describes this data is the orange line, the dashed line, but this is a very simple model and it doesn't really reflect the data very accurately. The green curve seems to much better capture what is happening, but it is also more complex. Machine learning algorithms derive these models from data sets by searching among a set of possible models. Often this is done with the purpose of being able to make predictions for the future. For example, what will happen after 2 o'clock? Or what will happen tomorrow? How many cups can I expect to sell tomorrow at 10 o'clock. But we can also actually, this is a very simple example, we can imagine that we could train the whole algorithm of the AI system on a lot of data. Systems like Google Translate, for example, are trained on millions of examples of text in both languages that are translations of each other, and they extract a complex model that allows them to translate arbitrary new text from or to the target language. The great advantage of machine learning approaches over knowledge-based approaches is that they are much more robust and can handle uncertainty. In a logic-based system, for example, almost any rule we can write down will be wrong in some special cases. The grass is not always wet because it has rained, but maybe also because every now and then a human waters it or the gardener comes. So you can imagine that when you're trying to write down human knowledge, capturing all possible eventualities is rather impossible. Machine learning approaches can deal with this uncertainty much better. They can apply soft criteria to make a decision that can reflect complex statistical distributions of the kind that we encounter in the real world. The real world is not clean and always rigid, and therefore you need sometimes these decisions to also have soft edges. Now, one important thing to say is that the more complex the thing you want to model, the more complex the models need to be that you are going to consider. Now, as you can understand, there are more curves than there are lines. So to decide which one best describes my data, I'm going to need more data to distinguish between those that might be quite similar. And the reason that has been behind the recent success of machine learning is therefore, to a great extent, that we now have vastly more data than we used to have 10 or 20 years ago, and also much, much bigger and much, much faster computers. So the methods have also improved, but the reason this became possible to be applied in so many ways was really this abundance of computing power and data. Now, the kind of state-of-the-art systems that we see today are largely based on machine learning techniques, but sometimes also use ideas from other areas of AI. And I want to give you a flavor of what is possible today by talking about a system that is called AlphaGo. It was developed by DeepMind a few years ago. And this solved a problem AI researchers considered unsolvable for a very long time, which is to write an algorithm that can play the game of Go better than human champions. Now, this is an incredibly hard game. It has many trillions of possible situations. But unlike chess or other games like checkers or poker, patterns are much more important than the actual specific positions of pieces. So you can imagine that on this board, if I care about what the shapes look like, then that is something that is quite easy to see for humans, especially for an experienced player, but it's quite difficult to understand for a machine. AlphaGo's success was in large part due to a technique called deep learning. This uses very large neural networks with many layers and millions of these simulated brain cells. And what it is used for in AlphaGo is to predict how good a position on the board is. So I want to be able, if I got into a situation, to say, is that a good situation or a bad situation? Because that can help me choose my move. Now, what these deep networks are particularly good at is to detect patterns at different levels of abstraction in each layer, where each layer defines its abstraction in terms of the previous layer. So you can imagine how you can start to identify shapes that are actually relevant instead of getting caught in looking at millions of different slight variations on this big board where there could be too many distinctions that you have to make. Now, AlphaGo combines this way of evaluating situations with another technique that's called reinforcement learning. And this is based on the idea of trying out different moves, working out whether they lead to a good result, and then learning to reproduce good moves and avoid bad ones. This is not too different from the way a rat learns to find cheese in a maze. I'm sure you have all seen these experiments. And in fact, these techniques have been inspired by theories of animal behavior to some extent. The third piece in the puzzle is an idea that is actually closely related to what I was talking about in the context of robots and planning. And that is the idea that because the game is too big to explore all situations all the way to the end to find out whether I will win or lose, you search in a statistical way a large number of likely behaviors of the opponent, and you don't go all the way to the end of winning or losing. You evaluate 3, 4, 10 steps ahead and consider whether it's worth searching deeper because this might be a particularly good path, or whether you can ignore this and should look in another direction. Now also, this is called game tree search, so you create a humongous tree of different things that could happen. And the system, in fact, also used millions of human games, which helped it focus more on things that human opponents are actually likely to do. So the reason I'm describing this example is to give you a sense that current systems still can do only very specific, narrow things when they do them very well. We have made great advances by being able to use lots of data, combining different methods, and trying to solve really hard problems in quite an engineering-focused way. Now let us switch gears and talk about something else, which is our own intelligence, and to think about what part tools play in our own intelligence, maybe so that we can better understand how we can shape our relationship to AI as a tool. So the first thing I want to talk about is what is our experience of human intelligence? And I want to ask the question of what do we base our understanding of intelligence actually on? Arguably, one part of this is introspection, that is experiencing our own thoughts, analyzing them, seeing what that feels like, and observing our actions. And I hope you will agree that that is rather vague. We might not even be sure whether our brains are tricking us, and what we think is going on is not actually what's going on. The other part of understanding what intelligence is, of course, how we talk about it, how between humans we observe things that look intelligent, and how we talk about it, and when we say that it is actually something we are observing. And in that respect, I would argue that most of the capabilities we consider to be unique to human intelligence, especially the impressive ones, things like writing a poem, playing chess, building a cathedral, conducting a science experiment, none of these things are actually things an individual could do on their own outside a pretty advanced society. Intelligence, at least those parts of it that we consider great human achievements, is, I would posit, a social and cultural phenomenon that goes beyond the capabilities of single individual human brains. Now, of course, if you want to use a metaphor of the brain as a computer, we could say that our collective intelligence, in some sense, runs on human brains, and that it is also augmented by the tools and technologies around those brains that we use. For example, the social interaction and cultural transmission of ideas, knowledge and skills is itself, in some sense, artificial, and you might even call it technological. It does not exist, with very few exceptions, in nature. So when we think about computers as tools and think about of them about having some form of intelligence, even in only very limited ways, I think rather than being kind of impressed by this magic, it might be useful to compare them to other types of intelligence that we actually already use. One example I really like is that of horses. We breed and train them. We train ourselves to be able to use them, and we use them to augment our capabilities. On a horse, we can do things that we can't do without a horse. Yet their intelligence, even though they are mammals like us, is actually not very much like our own intelligence. So in that sense, maybe they are not so different from computers. And maybe, even though they have, compared to a human, some limited form of intelligence, horses might be quite similar to computers in that they can do very specific things very well. Now, the human use of a horse's intelligence is also artificial. It has evolved over time, and the horses evolved as well. We kept changing them, and we kept changing ourselves. When they first appeared in America, in very impressive ways, Native Americans learned how to use them, even though it was not something that was around in their natural environment. That's an incredible achievement if you think about it, not just of the human brain, but also of human civilization, because some people started learning and then they helped each other and so on. So if you think about it, that's not so different from AI. As I have described in the beginning, us computer scientists and engineers, and maybe also you, the users or the people affected by this technology, learn how to communicate with those machines according to their capabilities. They are not 100% reliable or predictable, neither are horses, but they help us do useful things and make us, in some way, smarter. Clearly, as the AI systems we build will change, so do we by adapting to them. And this is not a new thing. It happens with lots of types of technology. Nobody is born ready to ride a bike or fly an aircraft. And so, because this is a new technology, it is certainly true that we must think about how it will affect the human experience, but I personally don't think that that is a fundamentally new phenomenon. Human experience has constantly shifted throughout the history of humankind as new technology was developed. Now, given that, and if you give some credence to the arguments I have put forward, then we might ask, why does AI really have this magical and mysterious appeal? My answer to this is very simple. I think this is mostly the fault of the AI community itself, of science fiction writers, journalists, the media, and other people who find this idea of replicating humans worth creating a mystery around and creating a magic around. The dream of replicating humans is very old. It appears in ancient mythology. It appears in lots of legends, from the Golem and Frankenstein to Terminator and modern robots. It seems we are intrigued by the thought of what would happen if we achieved that, because it goes to the very foundation of what we believe about ourselves in terms of our own humanity. It also seems to be some sort of hubris sometimes. We think that if we replicated ourselves, that might be dangerous or foolish. But at the same time, ironically or paradoxically, we are obsessed with the idea. I speculate that this is due to the very deep belief that we are unique and different from everything else in the world, but also that we want to understand what we are, which I think is rather natural. Interestingly, by the way, everybody talks about when robots and AI systems will be like humans. Now, replicating ourselves isn't actually that hard. We've been making other humans since the dawn of time. It takes 9 months, some incentives from evolution, and a bit of luck. And we can do that. And when we create humans, we shape them by interacting with them, sometimes against their nature. Who even knows anymore what their nature is? modern humans get born into a complex society, and therefore we could even argue they are built in some sense into an artificial world that we have shaped, not in a very different way from the ways in which we might build AI. And as the AI gets more complex, if it ever is as good as maybe not a human, but maybe a dog or a horse, or think your other favorite kind of intelligence that might be helpful, then there might come a point also where we don't understand exactly what's going on, and we deal with those new systems just like we deal with human people we don't understand, or just like we try to shape children as they grow up, but ultimately they become autonomous and they do the things they want to do, and that gives rise to all the wonderful and terrible things about being human. Now, what is tricky about AI, though, and I will admit this, is that in terms of how these systems look and how they are experienced physically, we can make them look very human-like. That can be convenient and useful, but I would argue it's also dangerous. It sends out the wrong message. It suggests that they might be like humans and that they should be approached like humans when they are, at least to the present day, not. No, so the one thing I would come back to, however, is that they are different from other tools because we can talk to them. And maybe that is actually the real innovation. They are unique in terms of having a language. And you could paraphrase Ludwig Feuerbach's famous statement about how man created God in his own image, and say that what is truly unique about AI is that we made it in our own image, as we are the only other species that uses language and is able to augment its intelligence by working with each other through society. Now, when we say communicating here, there are very different ways you do that. The programmer might do that through a programming language. The user might do that through their mobile phone. So how much this means we understand what's going on may really depend on the technology. Now, in the end, whether that will help us understand how humans work is an open question. Both of the schools of AI that I have described try to do this in some way, either by using our intuitions or by using or by taking inspiration from the brain. But as I've said before, in our day-to-day work as AI researchers, we don't really focus that much on whether what we are doing helps us understand human intelligence. And it's evidently clear that the intelligence we're creating is in many ways different from ours, and there's nothing wrong with that. We were inspired by birds to build airplanes, but when we built the airplanes, they were nothing like birds. Yet they are nonetheless very useful. So we take our knowledge about the world, try to imitate something, but we come out with something different. And along the way, you make errors. One big error AI has made is that we created inflated expectations many times. In the 1950s, people thought we would be done by 2000. Now we are here in 2022, and I can't even get a robot to unload my dishwasher. So this has led to a lot of these kind of hype cycles where there are inflated expectations, and then there are these so-called AI winters, periods of time where government, industry, and the general public completely lost faith in AI, and there was no longer funding or support for doing this work. So I think this is interesting and dangerous. One should always be realistic, but it is also not the first time this has happened. In the 1840s, railway mania took over England and Ireland, and over 9,500 miles of railways, when the railways were new, were supposed to be built. Only about a third of those were actually built. Lots of the companies were fraudulent. They didn't actually have the technology they promised they had, or they were just investment bubbles of people trying to make money. So in reality, what is happening often is that we explore new technologies, And then we learn how to deal with them after we make mistakes or after initial phases of confusion and exaggerated expectations. Nuclear power is an example where we learned to live with something quite dangerous, where accidents are very rare, but the price you might have to pay is very high and disastrous. We created regulation, safety engineering methods, government control, and we continue to debate them. We have in no way decided how we're going to use nuclear energy forever. Now, before we learned how to deal with it, we did some silly things. We used it, for example, to show to customers that they, X-rays to show to customers how well the shoe fits, right? So in the early stages of the technology, we often do stupid things. Genetic modification, many people argue, was handled poorly. People had concerns, and therefore a lot of development was stopped because the wrong messages were sent out, for example, by creating mice that glow in the dark, which isn't the most useful thing you can do with genetic modification, and maybe therefore we lost out on many opportunities where this technology would have been magnificent. So is AI different? Am I making my life too easy here just by saying it's just like any other technology? Well, it is evolving faster. It is widely accessible much more easily when something new comes out. And its impact might be quite subtle when you are watching an individual event, but it might be huge on aggregate. You may not think that, one more post on social media will create a big societal problem, but we know that on aggregate, sometimes these things have led to the manipulation of elections, for example. So there are clearly new risks, because these systems can make many decisions fast, because these systems adapt over time and they might change over time, and simply also because we are pushing them out too soon before understanding them. But do we need to be seriously worried? Many of you will be aware that there are big debates around AI and that people are really worried about the manipulation of elections through social media, concerns around face recognition and pervasive surveillance in the public space, the use of biased algorithms that underpay workers or put innocent people in jail, and worries around how people will lose their job as a consequence of automation and AI. Personally, I think the way this debate is going is that there is a real danger that the next AI winter, the next loss of public trust might be just around the corner. And that worries me, because I think it will prevent us from reaping all the benefits for humanity that AI has to offer. I think we have to acknowledge the problems we're seeing, but we also have to be aware that a lot of these problems are caused by a careless, sometimes you might even say reckless, tech culture, and that they often happen because things are developed and deployed before we actually understand all the risks about them. This is an ethical issue, but it is only to a smaller part, I would argue, an AI issue. The AI element triggers some of the problems. It is often a business issue, or a data ethics issue, or a privacy issue. So nonetheless, the AI may create new risks, but we really need to address the questions around products and services that are developed before we know that it's a safe thing to do, and thereby make an important distinction between research and real-world products, because we cannot stop the development of new technologies in the lab because somebody is doing something not very good with them in a way where they are behaving recklessly. In this area, many people are calling for regulation, but as I've explained to you, AI is extremely broad. I always say regulating AI is a bit like regulating algebra. Who knows what AI really is, what it will be, and we can't do the regulation without talking about where it's used. If it's used in crime and justice, That's a very different situation from using it in healthcare, or it's a very different situation from using it in manufacturing, for example. But I also think that there is a lot of kind of anxiety which comes from the fact that a lot of the debates are not mature enough. In many areas, the industry is not mature enough. It doesn't conduct a good risk-benefit analysis. The providers of the technologies aren't giving us the evidence we need to trust these technologies and to make informed decisions. And there is also still not enough education and awareness about how these things really work. Now, I want to conclude just with some final remarks that personally, I think despite all the risks that are inherent to any new technology in general, and those that are specific to AI, I firmly believe there are enormous opportunities for humanity to benefit from AI. For the first time in history, we have sufficient information about what is happening around us in the world, not only to understand complex phenomena in society and in our natural environment, but also to be able to make rational, evidence-based decisions and address some of the major global challenges we are facing. We can use AI to understand the effects of global warming and design technologies that produce lower emissions. We can improve food production and reduce poverty and diagnose and cure diseases, among many other things that I'm sure people will continue to develop. I've tried to make a case for looking at AI as an opportunity with a sober, critical, but optimistic outlook, and to embrace the idea that new technologies will require us to evolve alongside their evolution. Above all, we need to better understand potential benefits and harms, and we need to have informed, constructive debates that will guide how we actually learn to manage and navigate the risks that AI brings. I argued that the magic and mystery that surrounds AI doesn't really help in that regard, and advocated for looking at AI as a tool in the tradition of other products of our civilization that was to augment our intelligence. One should always be very careful when making predictions about the future. Who can really tell what will be? You will all certainly have different expectations and concerns about what role AI might play in our future. Personally, I'm excited that we will to see how we will make use of these new opportunities, and I hope that AI will make us become smarter in how we live, work, and treat each other. Thank you very much.
Drodzy Państwo, mamy niewiele czasu, 7 minut. Czy ktoś z Państwa chciałby zadać pytanie naszemu głównemu gościowi? Akurat 3 pytania, myślę, że dokładnie na tyle mamy czas, więc super, że się Państwo zgłosili.
Actually, Marvin Minsky is a co-author of a science fiction book with Harry Harrison, and the name Turing is in the title. But I would like to ask you a question. Strange, I think, that there are in nature some mushrooms that can mimic some flowers in such a way that they deceive, let's say, bees, both physically and chemically, and they land on them thinking that those mushrooms are actually flowers. Since I'm not neither biologist nor computer scientist, I'd like to ask, mushrooms and plants are different organisms. Mm-hmm. So even starting a process of mimicking is rather risky or non-obvious. Would you call such a strategy as, I don't know, intelligence? Mm-hmm. Mushrooms cannot think.
So if you think about intelligence in evolutionary terms, I'm sure that these mushrooms developed that strategy because it helped those who had that ability to survive. But we must distinguish with artificial intelligence, and it's important, thank you for the question, because it's important to make that distinction. Technology is not an outcome of the evolution of nature. We have no obligation to let it survive us. It is a tool that we develop and if we don't like it, we just throw it in the dustbin. And so the intelligence of things that are alive has mainly come from the fact that they needed to survive under evolutionary pressures with enemies and so on. And I would argue that if, like the mushrooms in your example, you show a flexibility of behavior that allows you to achieve a goal in a complex environment, for example, when the birds come, then that, I would say, is an expression of a very rudimentary type of intelligence. But there is also a danger in talking about that just because we see what has survived. We can certainly think about an even more complicated strategy, or we can say, well, the bird is certainly smarter than the mushroom, even though sometimes it gets fooled. So I think it's very hard to kind of put an intelligence rating on things. I think when we see how problems are solved in nature, or when we see how they are solved by a tool, the measure of intelligence for us should be how much benefit we get out of it. And by the way, I do not think that necessarily if the systems are smarter, they will bring more value. We use incredibly simple systems that do wonderful things and don't need to be any more intelligent than they are.
I have a question that may sound strange also, but I get inspired by your lecture. I was thinking, what's the main difference, in your opinion, between artificial intelligence and a human, actually? Because DNA is also a program, and I was thinking that also the artificial intelligence has its father and mother, I would say, and we also have this DNA from our mothers and fathers. And I think maybe the difference is that we have all senses that we use to, I don't know, discover the world and the rules and so on. So I'm very interested. What's your opinion on this?
So it's a very interesting point you make, and I really like the idea of the DNA like a program, because you are right. The information for how the body and the brain will behave, it needs to be somewhere encoded so that it can be transmitted from generation to generation, and that it can tell the cells what to do in order to get arms and legs and a brain and eyes and so on. So it is not that different in principle. But I think there are also, well, obviously the most fundamental difference is this is by orders of magnitude much more complicated than anything we could build with computer technology. For example, the human brain is much, much slower than our fastest computers, but we could not achieve the parallelism, the ways in which the synapses do things at the same time and are interconnected. They're so strongly interconnected with each other. I think somebody calculated even if we used all the cables in the world, we could not build such a thing. So I do think there is a real difference in terms of the scale and the amount of flexibility, intelligence, and adaptability. The other thing I would say is we don't know, we don't think of DNA as being actively designed with a specific things in mind. What I want to say, what I mean by that is the variations that have happened in individual humans are a very long-term search for something that can survive. It may be that our DNA contains lots of information that isn't actually needed, or that, you know, a programmer, a very smart programmer, could look at it and say, you know, this could be done much better, right? Why does this person get osteoporosis when they get older? We can fix this, right? So there is a difference between deliberate design, which is what we do when we write the programs. We think about, okay, what do we want to happen, and what will happen, and how do we design it, versus looking at the DNA. And I think parents, they wish they could actually say something about what they want their children to be like. Very often, a lot of it is luck. So, or maybe not. Maybe then they would be responsible. So maybe it is good not to be completely responsible. So, so I think on some level you can draw this parallel, but the level of complexity of humans. I mean, I would be happy if we reach the level of an ant. You know, I think human is like completely beyond.
Drodzy Państwo, jeszcze jedno pytanie było... O, właśnie, skupiłam Pana.
Thank you for the talk. It's very interesting, and I especially like the way you compared two schools of AI to two different schools of philosophy, and this made me think about some of the new AGI initiatives where they basically feed a lot of data from the internet into the system, and this data also includes rules themselves.
Can you just repeat, because it's a little bit not very
Can you hear me now?
Yes, that's better.
Cool. I was thinking about, in the context of this classification, about AGI, when they feed a lot of data into the system, and this data includes rules themselves as well, because they just scrape everything, right? And I wonder, how would you classify this? Is this machine learning because it's just learning on data? Is this rule-based because this data contains rules? Or that's something completely new?
So I have described this dichotomy because I think the key difference is where the knowledge comes from, whether it's explicitly put in by a human or whether it's derived from the data. Now, in reality, the dichotomy is never so extreme. So first of all, there is also no machine learning algorithm that is just completely generic. The designer always does some fine-tuning and does certain things to make it work better. Or sometimes it just sees that it doesn't work well and throws away some data that is not so good and so on. And now people are looking also, and this is why I also used the example of AlphaGo, because actually it is rather hybrid. There is a lot of knowledge about the game that goes into the design. You don't, as a colleague of mine, say take the parts of a watch and throw it on the table, and suddenly you expect that there is a watch. So I think, you know, in reality, it is not as extreme as I described it. And you mentioned AGI, artificial general intelligence. So there are efforts and people who claim they can create an architecture or a kind of system that could learn any kind of task. And I think what is happening there is that actually most people probably expect you will need both. Most people think that it will be a combination, but nobody quite knows how that works, and it will be interesting to see. I personally don't believe in this kind of general intelligence because I think we don't even know what this is for the human intelligence. You know, we can always find tasks that we are not good at. I mean, try to give me a basketball. I don't think I will exhibit very general intelligence. So I think we should stick to trying to solve specific things. I am not so certain we will have proven anything if we make a system so big that it does a lot of different things. And we can show that, look, there is one system that does all these things. But this is a personal opinion.
Dear Professor, thank you so much for the lecture. Zapraszamy Państwa z kolei na studio festiwalowe, które rozpocznie się dosłownie za chwilę.
Thank you very much.